All right, good morning, friends. Welcome to the last lecture of Call 202. Reminder that the major exam is going to happen on November 16 in the afternoon, 1 o'clock to 4 o'clock. Right, and I hope you must have seen my announcement about filling up this declaration, and I hope all of you will fill it before the deadline. Cool. So what is the plan for today? So the plan for today is to uh, go over the proof that we left off, or rather that we finished in a hurry in the last class. Let's go over it slightly slowly so that everybody understands it. And then I'll just discuss the relevance of this group theory into computer science. I'll discuss a very computer science type of problem, which is called the hidden subgroup problem. It's a computational problem. Uh, and then we'll see what kind of applications it has to more practical problems. Right. So I expect this lecture to be completely, rather, I expect it to be not too mathematical. I don't think I'll introduce anything new in today's lecture. Uh, right. Okay. So let's get going maybe. All right. So what were we doing in the last class? We introduced this notion of a group homomorphism, if you all remember. So let's quickly recap what we did in the last class. What is a group homomorphism? Suppose you have two groups. Let's say this is group G and its operation is the square operation. I'm trying to be consistent with what we did in the last class. And then there is another group H and its operation is, let's call it the diamond operation. Right? So a group homomorphism is just a function from the set G to the set H which satisfies certain nice properties, right? So phi is a homomorphism if what? So if for every x and every y in this group, right? So this gets mapped to phi of x, this gets mapped to phi of y, right? So what should happen for every x and every y? The quantity x square y in this group right should get mapped to exactly phi x diamond phi y in the other group. Right, so in other words, if G square is a group and H diamond is a group, function phi goes from the set G to H is a homomorphism if for all x and y in G, what do you have? Phi of x squared y is equal to phi of x diamond phi of y. Right, and then what did we see in the last class? We saw that image of phi is a subgroup of H. What else did we see? We saw that this kernel of phi. What is the kernel of phi? It is the set of right. So okay. Right. So let me draw another diagram maybe. Right. So you have a group. You have another group. Right. So the second group has some identity element IDH. Let's say. So the kernel of this phi is the set of all x in G such that phi of x is the identity element of H. Right, so it is some subset of G. Okay, so this guy is kernel of phi. Right, so we saw that this kernel itself is a subgroup of the domain of G. Right, and then the uh, the result that we did in a hurry in the last class was the following, right? So the question we are trying to ask is, well, here we started out with the identity of the H, identity of group H, and we looked at the set of all elements which map to the identity. Let's try to do this for an arbitrary element of the range of the image. So this image of F, image of phi. Let's take some arbitrary A in this image, and let us look at the set of elements which map to A. Right, so it's some other set. Right, so let's say all these elements map to A. Right, so the question is, does this set, let's call this set maybe C sub A, does this set CA satisfy some nice property? Right, just like the kernel was a subgroup of the original group, what is CA? Right, and right, so let me put down this definition. CA is the set of all x in G such that phi of x is equal to A. So this is defined for all, this is defined for all A in the image of phi. Right, so if A is not in the image of phi, then obviously the set is empty. That's not interesting. Right, and now the claim we were trying to prove in the last class is that CA is a left coset as well as a right coset of kernel phi. Okay. So let's try to do this slowly. Right. So let me just copy this claim to the next slide, and also maybe the diagram. Okay, so let's try to prove this now. Any question before we begin the proof? Okay, cool. Apparently no questions. Right, so what do we want to prove? First of all, we want to, right, so we want to identify, right, when we are trying to say that CA is a left coset of the subgroup kernel phi, we want to identify some element x such that x squared kernel phi is equal to CA. Right, so find x such that x squared kernel phi is equal to CA. So then if we manage to do this, then we have proven that CA is a left coset of kernel phi. Right, so I'll just prove that CA is a left coset of kernel phi. The proof that it is a right coset is completely analogous. I'll just leave that to you. Okay, so what x should we start out with, right? So remember, A lies in the image of phi, right? So what does that mean? A must have some pre-image, right? Excuse me. Okay, so A lies in the image of phi, right? So therefore, there exists some x in kernel. There exists some x in G, such that phi of okay. Let me use a right. Okay, fine. So there exists some x in G such that phi of x is equal to A, right? And now I want to claim right? So what is our best hope? Let's use exactly this x and show that this claim holds. We claim that CA is equal to x squared kernel phi, and which is also equal to kernel phi squared x. But yeah, I'll leave this for you to figure out. Right, so now what is x squared kernel phi, right? By definition of a coset, so recall x squared kernel phi is the set of all what? All y in G, right? It's the set of all elements of the form x squared little h such that this little h is in kernel phi. Right? This is the definition of the left coset. Okay, so now what does this, right? So what is this equivalent to? So this claim is equivalent to proving that for all y in G, right? What do we want to prove? Y belongs to CA if and only if y belongs to x squared kernel phi, right? So y is in CA if and only if y belongs to x squared kernel phi, which means there exists some h in kernel phi such that y is equal to x squared h. Right, everybody with me up to this point? Okay, so let us prove both directions separately. So let us maybe do the right to left direction first, right? So there exists, we are assuming that there exists h in kernel phi such that y is equal to x squared h. And now what do we want to prove? We want to prove that fy is equal to a. So actually let me just put it that way. So instead of writing y is right, so this is right, so this by definition is same as saying fy, okay, phi of y is equal to a, sorry, by definition of CA. Right, so what is phi of y? This is just a one-liner, right? Because phi is a homomorphism, phi of y, which is equal to phi of x squared h, is just phi of x diamond phi of h. Right? Now what? So phi of x is a. Right? So this is equal to a diamond, and h lies in the kernel of phi. Right? So therefore, by definition, phi of h is nothing but the identity element of h. Oh, let me not confuse you. Yeah, let me just rename this h to a g, right? Because we also have a completely different group, capital H, right? So let me just make it a g. There exists a g in kernel phi. Right, so this is just a, right? So therefore we have phi of y is equal to a, so therefore y is in CA. And let us prove the forward direction now, which is equally easy. Right, so y is in CA. So okay, so what is right, so we need to finally get hold of this g, which is in kernel of phi, right? Such that y is x squared g. Right, so what should our hope be? So this is same as saying y, right? So this is same as saying y. Okay. This is same as saying x inverse square y is equal to g for some g in kernel phi. Right, I'm just pre-operating x inverse from both sides, on both sides. Right, so let me just say x inverse square y is in kernel phi. This is what we want to prove. Right, if we manage to prove this, then we are done. right? And then again, that is also easy. What do we mean by x inverse y belongs to kernel phi? We just need to take the phi of x inverse square y and prove that it is the identity element of the group H. Right, but because phi is a homomorphism, what do we have? This is just phi of x inverse square phi of y. But in the last lecture, we saw that if phi is a homomorphism, phi of x inverse is phi x ka inverse. Right, so this is phi x inverse diamond. Oh, there should be a diamond over here, right? Diamond phi of y. Right, so this is nothing but A inverse diamond A, which is IDH. That's it. So therefore, x inverse squared y, x inverse square y belongs to kernel phi. But what do we have? But y is equal to x square. Let me, yeah, x square x inverse squared y, which is by associativity equal to x square x inverse square y, right? So this guy is in the group H, is in the group kernel phi, right? So therefore, y is in x square kernel phi. Right, so that way we have proved that if y belongs to CA, then y belongs to x square kernel phi. Right, so it's just a one-liner. It's just a matter of parsing what we are trying to prove. That's all, and using the basic group properties. Any question?
There I have a slightly unrelated doubt.
Yes,
Basically, for all abelian groups, we have that left coset is always the same as right coset, right? So,
right.
but the converse is not true, right?
Converse is not true. Yeah, for a non-abelian group, you could very well have a subgroup which has the property that every left coset of that subgroup is also a right coset. Right, and as soon as you have such a homomorphism from this group G to some group H, you can identify one such subgroup. Okay, Samyak?
Okay, I was just thinking.
Yeah, sorry.
I was just thinking of what you were saying, the example. I was just trying to figure it out.
Okay. So what does this mean? This means that if, right, so what does this mean? Corollary, every left coset of kernel phi is also a right coset of kernel phi and vice versa. Right, and then each such coset is the set of pre-images of a fixed element in the image of phi. Right, so how do you, okay, so here we just proved that CA is a left coset of kernel phi. How do we prove it is a right coset? There will be one little trick that is happening over here. Right, where will the difference happen? Right, so this proof will be exactly as it is, except that you will have g square x in place of x square g, and here you will have IDH diamond A instead of A diamond IDH. And over here you will have to, I guess you'll have to just consider y square x inverse instead of x inverse square y. That is the only difference. Okay, so right, so let us see a nice computer science application or relevance of group theory to computer science. Maybe that is a better way of putting it. Right, so I'm going to discuss something called the hidden subgroup problem. Right, so maybe I'll start with the next slide. Okay, so what is the hidden subgroup problem? Okay, so here is the setup of this problem. Right, so let's say you have some group G comma star. For simplicity, let's just assume it's an abelian group, commutative group. Also known as abelian group. And mind well, it's a finite group. Finite commutative group. Okay. H is a subgroup of G. Okay. And we have the third component, which is S is some set S. S is some arbitrary set. And finally, the fourth component is some function f going from G to S. Now, this is not some arbitrary function. This function satisfies some nice property. What is that nice property? The nice property is, right, so for all x, y in G, right, you have fx equal to fy if and only if x and y lie in the same coset of H. Right, so let's draw a diagram. This is your group G. This is your subgroup H. And these are the cosets of H. Right, so remember H itself is a coset of H. And now F is going to take a group element to some element of set S, such that everything in any given coset is taken to the same element of S. And two elements of G which lie in different cosets are taken to different elements of S. Or in other words, F is constant on cosets of S. Or F is constant on cosets of H. So one such example is exactly this function. Right, so a homomorphism is one function which satisfies this criterion. Although in the hidden subgroup problem, H the codomain of this function need not be a group. It need not have a group structure, and obviously it makes no sense to call this function a homomorphism. It's some function. But the critical property is that it is constant on cosets of some subgroup of G, which is that group H. Right. So what is given to us, right? So it's a hidden subgroup, right? So somehow the name suggests that, okay, this group H is subgroup H is hidden and we need to search for it, right? So let us formalize that. So what is given to us? Right, we are given a black box which computes this star operation. Right, so you have some black box, you feed in two group elements, out comes one group element, which is, right, you feed in x and y, out comes x star y. Right, and similarly you have a black box computing, you have a black box computing f, which means, right, you feed in a group element x, out comes f of x. Right, so these two black boxes are given to you. Now you need to kind of execute queries on these black boxes, and you want to, your goal is to find H, find this hidden hidden subgroup H. Okay. So does somebody want to suggest a trivial way of doing it? A very basic way, the first thing that you will try?
Compute F for all elements in G.
Okay.
And then you like group them up on the basis of the output. The one which contains the identity will work.
Nice. Nice. Right. Right. Very good. Right. So the trivial algorithm. So the trivial algorithm for doing this. Right. So for all G in the group capital G, find F of the group element. Okay. We call this X. For all X in capital G, find F of X. Right, and now what is the subgroup H, right? So obviously remember the identity element of G is always going to belong to the subgroup H, that is for sure. What other elements are going to belong to this subgroup? So this subgroup itself is a coset, right? So an element is going to belong to this subgroup, element X is going to belong to this subgroup if and only if F of X is equal to F of ID, right? So H, so output H is equal to the set of all X in G such that F of X is equal to F of ID. Right, so this is a trivial algorithm. How much time does this algorithm take? Assuming that these black boxes return you their output in unit time, unit amount of time, this takes time order G, order size of G. Yeah, Divyanshu, your hand.
Yeah, sir, in this problem, are we given that what is the ID of the set, or do we need to first find that also?
Good question. Do we need to first find that also? Oh. Right. Let's assume that you are given the ID. Okay. So let's be concrete about this. Let's assume that the elements of G are encoded as some bit strings of some fixed length, and all zero strings is the ID of the group. Let's just make this assumption. Okay. Yeah. Somebody was asking something.
Sir, I think you can also just find it using, because you have the star operation, you can find it using mod G by checking every element with some fixed Y or something.
That will take order G steps, right?
Yes, it will take order G only, so it's order G only.
Sure. So what we are trying to do is we are trying to beat this trivial algorithm. Right, and in order to beat that trivial algorithm, it will be crucial that we know the identity element already. Okay, so let's just assume that you know the identity element, which is, let's say, the all zero string. Okay, so what is our goal? So our goal is to get a much faster algorithm than an algorithm which is linear in the size of the group. Right, so remember, if the size of the group is roughly 2 to the power n, then every element of the group can be encoded using n bits, and then this will be right. So we are playing around with n bits every time. You are feeding 2n bits, getting n bit over here, feeding n bits, getting some whatever size of s, log of size of s many bits, and so on. So basically, this will really be an exponential time algorithm. So which is why we are not happy with this. Okay. Right, so we want an algorithm running in time big O of log of size of G to the power some constant. Right, so this will correspond to something like a polynomial time algorithm, right? And under the setup. Yes, Ramanuj.
So is this log size of G to the power some constant analogous to size of S?
Not necessary, right? Because what if H is just the singleton identity element, right? So then size of S is must be at least size of G, right? Do you get the point?
Yeah, got it.
Right. So size S is something. Let's not just think about S, right? Right. So let's just assume that S is a reasonably small size set. Okay. So we want an algorithm which runs in time, polynomial in the logarithm of the size of G. Okay. So this problem, unfortunately, is believed to be hard on classical computers. So what is a classical computer? The kind of computer you and I work with. Okay. So it is believed that probably such an algorithm doesn't exist on classical computers. But on quantum computers, which is this mysterious object none of us has any idea about, which hopefully we'll get to learn in due course. Towards the end, in another maybe 3 years, you'll get to do a course on quantum computation, an elective, and then you'll come to know what is a quantum computer, how does it work. Probably some of you have some idea. Okay, that is possible. But whatever that mysterious quantum computer object is, that can do this job. That can find this hidden subgroup. That can solve the hidden subgroup problem in this much amount of time. Okay, so fact. Right, so fact. This is believed to be hard on classical computers. But quantum computers can do this. Okay, so basically, in order to understand how this is done, you first obviously need to understand what are groups, right? Otherwise, it's just not possible. Cool. Okay. So now, assuming that, okay, let's just assume that you have a quantum algorithm which does this, and let's try to see whether you can use that algorithm to solve more practical problems in computer science, right? So this is like a heavy hammer which we will use to solve several other problems, and we'll just see one or two of them in today's class. Yeah, Divyanshu?
So like the running time which we are expecting, so like won't it be at least order of mod h, like the size of h?
Good. Won't it be order of size of mod h? Actually, no. So when we are saying find h, what we actually expect is, okay, so it is sufficient to find a set of generators of h, although we did not define that. So we want to find, okay, so more precisely, find some subset, what should we call it? Find some subset, find a subset. There could be several such subsets, T, which is subset of H, such that the smallest subgroup of G containing all of T is precisely H. Right? So we are not explicitly finding H. We are just finding some small subset of H with the property that the smallest subgroup of G, which contains all of T, is necessarily equal to H. Right? And then turns out that you can have such a T whose size is logarithmic in the size of H.
Okay.
Okay.
Yeah.
Right. So let's not get into all these details. Let's just assume that you get H somehow. Okay. Let's be simplistic about it. Okay. So now how do you use this to get more interesting algorithms? right? So here is another problem, right? So order finding. So what is the order for finding problem? Your input is a number n and a number x such that GCD of n and x is equal to 1, right? So your input is two numbers which are co-prime to each other, right? And now remember that by Euler's theorem, what does this imply? This implies that x to the power phi of n, the Euler's totient function of n, is congruent to 1 mod n, right? So I mean, let us recall everything that we studied in that context, right? So okay, so recall that if you consider the set of all numbers from 1 through n which are co-prime to n, that we denoted by Zn star, right? So this is the set of numbers in 1 through n which are co-prime to n, right? So this Zn star under the multiplication modulo n is a group. We saw that in the last class, I believe, right? And moreover, we know that for all x in Zn star, right, what do we have? We have by Euler's theorem x to the power of this phi of n is equal to 1 mod n, right? And then therefore there exists some, right? So if r is the smallest, r in the set of natural numbers is the smallest one, number such that x to the r is congruent to 1 mod n, then r divides phi, right? So I think we saw that this also. Okay, and this r is called the order of x. The order of x in the group Zn star, right? So I hope we defined this. Okay, so so just wanted you to remember this. So now the computational problem is the following: you are given n and x such that GCD of nx is equal to 1, which means there exists the order of x in Zn star is well defined, right? So we want as output we want r the order of x in Zn star. Okay, so how would you do this, right? What is the obvious algorithm in this case? Somebody? Yeah, Rishabh?
Like the obvious algorithm would be just to calculate x to the r for all r.
Right, and pick the smallest one.
Yeah.
Right. How much time would it take?
Order of phi n.
Fine. Assuming your arithmetic operations are done in unit time, then it's going to be order of phi n. And remember, phi of n could be almost like n, right? So if n is a prime, for example, phi of n is going to be n minus 1. Right? And remember, so if these are some m-bit strings, this phi of n time algorithm would be an exponential time algorithm. Right? So obvious algorithm runs in time order phi n, right? So which could be order n, right? For example, if n is a prime, and so this is exponential in input size. Rishabh?
Yeah, so I have the reduction to the hidden subgroup problem.
Awesome. Okay.
So, like, should I say it?
Sure. Okay.
Yeah.
So one sec. So I think Rishabh's plan is to use this hidden subgroup, the algorithm for the quantum algorithm for the hidden subgroup problem, to solve this much faster than order phi n time, right? So let me just state it as a goal. So our goal is to get an algorithm running in time, big O of log of n to the constant. Right, so let's just assume that x belongs to the set 1 through whatever. X belongs to Zn star. Otherwise, in time linear in X, you can just find the remainder of X modulo n, and then just process that remainder instead of X. Okay, so that won't take much time. Good. Okay. Yeah. Carry on. Somebody was telling the answer.
Yeah, so I'll use the notation we used earlier. We'll use G to be the set of integers modulo phi n.
G to be the set of integers modulo phi n. So G is really the set 0, 1 through phi of n minus 1. Right? And then your group operation star is just addition modulo phi of n. Okay? This is your group.
Yeah.
Then what?
Your set S is the Zn star.
Okay, Zn star. Okay.
And your function f is x to the r. Fr is equal to x to the r.
F of what? R
is equal to x to the r.
Okay, let's not overload this R, right? R is the order of x in Zn star.
Okay.
So let's say f of y is what?
X to the y mod.
X to the y
Modulo n.
Modulo n. Right. So x is this fixed number in Zn star. Y is some number in the set 0 through phi n minus 1, and Rishabh is defining f of y to be x to the power y modulo n. Okay, so now why is this correct? Right. So his secret will give this as black box inputs to the quantum algorithm to find the hidden subgroup, and then that hidden subgroup is going to tell us the order somehow. Yeah, go on.
Yeah. So all the multiples of R get mapped to 1. So
okay, good. So his observation is that right. So the observation is that x to the power y is congruent to 1 mod n if and only if r divides y. Right?
Yeah.
Right, good, okay.
And yeah, so that's basically the main thing. Now, if you now all the left cosets will be like
what is the subgroup in the first place? What is the subgroup?
The subgroup is
What
all
is
the
hidden
multiples
subgroup
of
in this
R.
case? All the multiples of R in the set 0 to phi n minus 1. Good. Right. So H is the subgroup 0, R, 2R, and so on up to what?
Phi n minus R.
Phi n minus R, I suppose. Right. And then the group operation is just addition modulo phi. So this is a subgroup. And now Rishabh claims that f is constant on cosets of the subgroup. Right? Why is that, Rishabh?
So if you have a number f s plus k to the k into r.
Okay.
Then it maps to x to the s plus kr, and we know x
One
to the
sec.
kr.
What do we want to prove? What do we want to prove? We want to prove that, right? So
Uh,
first of all, what are cosets of this group?
Yeah, the cosets of this group will be all the elements which are a constant shift from the multiples of R. So
Correct.
all the
Correct.
sets KR plus S.
Correct. So you mean to say that y1, y2 belong to same coset, if and only if y1 minus y2 is a multiple of I. Good. And now what? So now what do we want to prove? If we want to prove that y1, y2 belong to the same coset if and only if f of y1 is equal to f of y2. Right? So if y1, y2 belong to same coset, let's say y1 is greater than or equal to y2 without loss of generality, so then what do you have? So then you have x to the y1 minus y2, right? So this is y1 minus y2 is a multiple of r, so therefore x to the power y1 minus y2 is going to be congruent to 1 mod n, right? So therefore x to the y1 is congruent to x to the y2 mod n, right? So which means if two inputs are from the same coset, then the value of the function on both inputs is the same, right? And what about the converse?
And conversely, if x if x y1 is equal to x y2, you'll have x y1 minus y2 is congruent to 1 mod n, and we had the observation that
X to the power y1 minus y2 is congruent to 1 mod n. When you said that, you are using some critical property.
x is like it's a subgroup. It's a group. Like S is a group.
X has an inverse, right? X has an
X is
inverse.
inverse.
X has an inverse in the group Zn star, right? So if you multiply by x inverse to the power y2, right? What do you get? X to the power y1 minus y2 is congruent to 1 mod n, right? So therefore,
Then with the observation.
R divides y1 minus y2, right? So therefore, y1 and y2 belong to the same coset. Right? Very nice.
Also, I had a question here. So here we computed phi n and didn't talk about it. So
We computed phi. When did we compute phi?
so while defining G, so as such, do we need to say compute phi n if we are converting it into a an instance of the hidden subgroup problem, because we define G to be 0 to phi n minus 1.
Okay. I see what you are trying to say. One sec. Do you need to compute? Right. One sec. Good question. Do you need to compute this? Yeah, I need to think. How do you get around that when you're using quantum computers? Right, because then the question is, how do you really compute phi n? Right, given n. But do you really need to compute this addition modulo phi n anywhere in the algorithm?
I'm not sure, because it will depend on the way the computer solves this problem. Because if it internally uses the star operation somewhere, then we might need it.
Right. So yeah, I'll have to find out. How this. Yeah, good point. I'll have to find out how is this handled exactly. Okay, fine. So don't worry too much about it. So this will not have this in the exam at all. This is just kind of some motivation. piece to kind of complete the whole discussion and show how it is relevant to computer science. So don't worry about this. Yeah. So this one little piece, missing piece that I need to figure out. Sure. Okay. But the point is, if you have an algorithm for, if you have a as soon as you have a quantum algorithm for the hidden subgroup problem, you have a quantum algorithm for finding this order. Yes, Aval, you had a question, I suppose.
Sir, what was the problem? Can you repeat that?
The order finding problem?
No, that phi and that we need to compute.
So his the complaint which I think Rajat had was that in order to use the quantum algorithm for the hidden subgroup problem, you need to provide the star operation as a black box, and you need to provide the f as a black box. So computing x to the power y is easy. That's not, by repeated squaring you can kind of do it efficiently. That's not a big problem. How do you provide this addition modulo phi n as a black box without actually computing phi n? Or do you need to compute phi n? And if you need to compute phi n, how do you compute phi n? Right? Remember, all that has to be done in log n to the power constant time.
Okay.
Right? So that's something I'm not sure about. I need to find out.
Sir, just one point. I'm not also very sure about this, but as far as I remember, maybe quantum computers can factor numbers in logarithmic time.
I'm coming to that point, but this is a part of factoring. So you will use this order finding to design a factoring algorithm.
Okay.
So you really cannot use the factoring algorithm to find phi of n.
Okay. Okay.
Okay. Or maybe there is some recursion happening over here. I'll have to find out the details. Yeah, I admit I completely missed this point. Okay, yeah, and then exactly, yeah. So this basically this gives a fast quantum algorithm to find the order of an element x in Zn star. Okay, and then as Aval said, right, so this order finding, so I'll just state this as a fact. I'm not going to go into the details. So fact, so fast algorithm for order finding implies a fast algorithm for factorization. For order finding implies a fast algorithm for prime factorization. So what is prime factorization? You are given as input a number n, you need to output the prime factorization of n. Okay, or I mean, it is sufficient to kind of either say that n is prime or split n in as a product of two numbers. Right? As soon as you can do this, you can further recursively split those numbers, factorize those numbers, and you can get the prime factorization. Right. So let me just put this in a parenthesis. So yeah, I mean, as soon as you have an algorithm for factorizing, you have an algorithm for prime factorization also. Good. And then this algorithm is right. So this algorithm for prime or for factorization, which uses a fast algorithm for order finding. So this was designed by a person called Peter Shor, and therefore it's called the Shor's algorithm. Yeah, obviously we are not going to go into the details. That's too much for this course, way too much. But if you take a course on quantum computation, you will definitely get to see all this. Okay, so that pretty much ends the technical part of this course. I just wanted to make a couple of concluding remarks, and then if time permits, I think time is going to permit, we could use the remainder of the time as a office session, or we could end early, whatever the class prefers. Right. So I personally enjoyed teaching this class a lot. Unlike my previous online courses, any of my previous online courses, this was much more interactive, and I'm really happy about that. So thanks a lot to everybody who actively participated in the discussion of the class. Tutorials, I admit, this was not the best way to conduct the tutorials, but given this restriction of conducting them online, I could not figure out a better way, unfortunately. So if right, so in future, whenever I teach this course, hopefully everybody is going to be in class, and then I plan to conduct a class tutorial where the TAs and I, or rather we give problems for you to solve, you can collaborate, discuss, and the TAs and I keep a watch on you, try to help you as much as possible and so on. So that is the plan for the next offering of this course by me whenever that happens. Okay, major exam, yes, so major exam, right. Major exam November 16, 1 o'clock to 4 o'clock. So it's going to happen within this interval. So this like the superset of the interval in which we'll have the major exam. There are couple of logistical, lots of logistical things that need to be figured out given the uncertainty of, especially of how many people are going to take the exam in person and how many of you are at home. So I will try to figure these out as soon as possible and keep announcing things. Your duty is to keep an eye on the announcements. Just be updated with the latest announcement. Okay.
So what will be
Right,
the time
so-
duration for majors?
Major, I'm planning 2 hours.
Okay, sir.
2 hours within this interval of 3 hours.
Yeah, okay, sir.
Yeah, I'll announce. Yeah, so basically it's going to be 2-hour exam. So it's going to be about twice the size of a quiz, although it will be a 40 marks exam, right? So the amount you'll have to write will be twice the amount that you typically write in the quiz, but the number of marks are 4 times. Just bear that in mind. Right. So everybody, whether you are in the classroom or whether you are at home, irrespective of all this, everybody types on Gradescope. So if you are going to take the exam in the classroom, you need to bring your laptops to the classroom. Everybody uses the same set of resources, your own lecture notes and whatever, lecture slides and blah, blah, blah. You know all that. I don't need to repeat. Right. All right. What else? Study well, write clean answers as far as possible. Right. Wish you all the best for all your major exams, not just Call 202. I hope all of you come back to the campus very soon, and I get to meet you all. Fine. So yeah, that's all I wanted to say. We have about half an hour, 30 minutes. So we could have this as a office 30 minutes, or we could stop here. I also plan to conduct right. So today evening we are going to have a tutorial session like every Thursday. One day before the major exam, which is Sunday in the evening, I am also planning to conduct a tutorial, extra tutorial plus office hour, in case that's going to help you all. Right, and then if you here is one gentle request to all of you. If you want to ask me something by pinging me personally, you should feel free to do so, but preferably do it by Sunday. Monday, it's going to be very hard for me to respond to your queries quickly. Right, so Monday there are lots of logistical things to be figured out to conduct the exam. So just assume that I'm not going to be available on Monday, except for the office hour. All right. So now let me stop recording unless there is some technical question before I stop recording. Any question related to groups or anything that we did in this course?
Sir, like I had this
Yeah,
stored up. Can we claim that like suppose H is a subgroup of G, then the cosets of H other than H won't, like none of them would be a subgroup.
You can, because none of them is going to contain the identity element. It's a partition.
Yeah, okay. This is trivial. Sorry.
Yeah. Anything else? Okay, we have a decent turn up given that this is the last class, 33. Okay, cool. Okay, right. So I'll stop recording now, and then I'll hang around in case you want to ask anything, or you should feel free to leave anytime. Right, so it's completely up to you.